Okay, today I'm going to talk about the shape of a hypersonic flight vehicle and how its passage through the air affects the Mach number distribution in the flow field surrounding the vehicle and the associated velocity distribution, and how that drives the shape of the shock around the craft. The shock shape is fundamental for working out how a hypersonic vehicle is going to behave, and what I'll give today is an approximate technique for some simple sharp body shapes which enables us to do these sort of calculations very quickly. And also I think that by focusing on the fundamental mechanism that drives the shock shape, we are able to understand a bit about the most important processes that are driving a hypersonic flow field. I'll start by talking about Mach number and how it interacts with speed. Of course, the relationship between speed and Mach number is very simple. Speed is Mach number times sound speed. So if your sound speed's constant, then velocity is directly proportional to Mach number. Of course, on a typical flight path, temperature does change throughout the atmosphere, but we'll ignore that for the moment and assume we're flying at a situation where the gas temperature is constant at 250 K, sound speed's about 317 meters per second, and as you can see on the curve displayed in this slide, Mach number, velocity in blue linearly increases with Mach number, and the associated total enthalpy, which is a combination of your velocity, your kinetic energy through velocity, and the sensible heat through the Cp dt term, is plotted as a red function. Now it increases primarily with velocity squared, which is proportional to Mach number squared. Because at the hypersonic flights, your velocity squared term is much bigger than your specific heat terms. So that's what happens as you accelerate along a flight path, or decelerate if you like. However, if you're considering flight at a constant Mach number, the velocity doesn't increase in proportional to Mach number because you've got h naught is fixed at, say, 2 kilometers per second. You've got 2 megajoules per kilogram of energy, and no matter how much you increase your Mach number through the flow distortions around the flight vehicle, it'll asymptote as Mach number goes to infinity to a finite value, which we can calculate quite easily. So the same relationship applies here. Here I've extracted velocity, that equation on the left, to indicate that it goes with the square root of total enthalpy, and I've plotted it against Mach number. Here I've normalized the velocity by the square root of the total enthalpy in order to have a truly non-dimensional graph that will apply at any time. This is done for a gamma of 1.4 for air. Well, one thing you'll notice about this curve is that, as I said, it asymptotes to a high value, but also as the Mach number's hypersonic somewhere above about 5, there's really very little velocity increase you get as the Mach number increases again. So if you look at the left, this might represent the flow field around a body at a given Mach number. As you go through the shock wave, the Mach number is slowed down again. Of course, the speed of sound increases as you slow it down because you're converting kinetic energy to heat. So the velocity doesn't drop as much as you might think it would. And if you're expanding around, say, a blunt body, the Mach number soon accelerates again up to a hypersonic value. And if you're in a very sharp body, a sharp wedge, you won't have that little subsonic region behind the bow shock, which we've shown in this figure here. Important point to note, though, is the velocity is not really changing much for a Mach number bigger than about 5. If we put some real numbers now, forget the non-dimensional stuff, going up to Mach 25, which is what you need for orbit, in low Earth orbit, we're talking about velocities of 8 kilometers per second down to 700 or 800 meters per second at the lower speed. And again, the same feature is evident. Above Mach 5, the velocity is not really changing much due to Mach number. For instance, you might be expanding the flow around a trailing edge of a wing to very high Mach numbers. They can go up to infinity, theoretically, as the temperature drops to 0, but you don't get an infinite velocity. It asymptotes out to a speed which is all you can go considering the finite amount of kinetic energy, or energy in any form, that's contained by the stagnation enthalpy. So this turns out to be a very useful phenomenon for us, because really no matter what you're doing with a Mach number, all the particles of gas traveling around the vehicle are going at approximately the same speed. So I can summarize this by saying there's very slight change in the absolute streamwise velocity of the flow, provided it remains hypersonic. This, of course, doesn't apply in the subsonic shock layer behind a normal bow shock, but if it's a sharp wedge or a cone, it certainly applies. Velocity doesn't change very much. And the primary phenomenon of a gas experience is that it's pushed sideways. The vehicle has to push the gas out of the way to fly through, and that's the effect which dominates what the Mach number will be and what the pressure will be, and also ultimately what the shock shape will be. And you can summarize this by saying plane sections remain plane. This means effectively that plane sections before the flight vehicle arrives will still be plane approximately when the vehicle flies past, because the velocity perturbations applied are not that different for different parts of the flow field. Okay, so in this slide we're considering a section of gas on the left-hand side before the vehicle arrives. Then it convects towards the vehicle and goes through it. It's getting slugged sideways by the displacement of the surface, but as we know now, its axial velocity isn't changing very much. So if you look at the points in this plane as indicated by the circles, they travel through the flow field past the shock and away from the nose at approximately the same speed. It's only when we get down to the subsonic boundary layer attached to the vehicle that it slows down a lot. So you can consider this as though it's happening in one plane. Okay, so the particles of gas that get processed by the shock or by the passage of the vehicle see a sudden transverse acceleration. Because they don't really know what caused that, because their axial velocity doesn't change much. It could have been caused by some explosion taking place in stagnant air, or it could have been caused by the passing of a hypersonic flight vehicle. So we're going to use this sort of similarity to analyze the situation in a hypersonic flight vehicle by pretending it was caused by some other phenomena which was taking place in a single plane. So in the plane of the slug of gas that we're interested in, we postulate that there's, say, an explosion or a shock wave, a piston that suddenly moves, which has the same effect of the passage of a flight vehicle, which is basically to push the gas out of the way. And in fact, this is useful to do because there's a large underlying body of knowledge about how these things work, say in the explosives industry or the shock tube industry, which we can use to get a simple and quick solution for the flow field around one of these vehicles. We look at it now, say, in the two-dimensional situation. On top here we have a representation of a sharp wedge flying through the air. It's supporting an oblique shock wave, shown in red on the top. And of course, the main thing that the gas notices is it gets pushed out the way sideways. It accumulates a transverse velocity. In fact, the velocity it gets is equal to the vertical velocity of the surface at the appropriate part of the flow. And we could also have done this by imagining, say, there was a shock tube which fired its piston at a given velocity. Immediately the flow arrived, and as it convects down in the flow direction, the passage of the piston represents the surface of the vehicle, and the passage of a shock wave down the tube represents the bow shock on the body. So in different series of time, we have the piston traversing the path of the vehicle and the shock wave created in the shock tube creating a locus of where the shock wave would be. I've drawn it there as an XT diagram because they're commonly used in shock tube technology. So you can see that the XT diagram of a one-dimensional shock tube is reproducing the bow shock location of a real flight vehicle, with the approximation noted that, of course, the velocities aren't exactly constant as we'd assumed before. But we'll do an example to show how important that is. Let's look at a flow travelling at 5 kilometers per second with a wedge angle of 8 degrees. You can see from simple geometry that the effective piston velocity will be the tangent of that angle 8 degrees times the flight velocity, which we've chosen to be 5 kilometers per second, and we get a number of 703 meters per second. So what this means is that if we had a one-dimensional shock tube and we accelerated a piston instantaneously to 703 meters per second, and we watched the progress of that shock wave down the tube, and then we took that shock wave, not the shock wave, we took the shock tube and we ran with it very fast at 5 kilometers per second, so it was mimicking, if you like, the passage of the flight vehicle. The locus of that shock wave in your moving laboratory situation would exactly match what had happened to the shock wave caused by the hypersonic vehicle. In fact, the gas couldn't tell if it had been done by some idiot running around with a shock tube in their hands or a flight vehicle passing through. Okay, so we'll pretend that this oblique shock we see in a flying vehicle was actually caused by a shock wave produced in a shock tube, and then we were moving with this shock tube in the flow direction such that the passage of a piston that was driving it exactly matched the trajectory of the surface of the flight vehicle. So when we do that, of course, the passage of the shock wave produced will map one-to-one onto the trajectory in space of, or the location in space of the shock wave produced by the flight vehicle. What we have here is a one-dimensional shock tube problem we have to solve, which you can do quite simply, either through solving exactly your shock wave relationships or using tables for shock wave flow. And the answer you get is a piston moving at 702 meters per second will drive a shock wave of 892 meters per second through air at 250 degrees. So now we can use that to find the shape of our shock wave in the flight vehicle. So we get a shock angle here, it's going to be the tangent of 892 over 5,000, which we get an angle of 10.1 degrees. That's the shock angle that will be supported by this vehicle at that Mach number, or the Mach number corresponding to 5 kilometers per second. We can also check this. We didn't really need to do this approximately. We could go and do it properly. When you do that, you find the number is 10.4 degrees. So the approximation inherent in this analysis is we get an error of 0.3 degrees and a shock wave angle of 10 degrees. It's not exact, obviously, but it's a useful thing to do very quickly. But also more important from my point of view is that it gives an illustration of what's the main mechanism happening here, what's driving this shock wave. And basically it's the fact that the vehicle flying through the air has to push the gas out of the way like a frog. And it's the velocity, the transverse velocity which it pushes it away, defined by the speed and the angle of your nose cone, which determines it. And of course we don't use this technique that much anymore. We have computers that can do it much more accurately, and it doesn't really take that long. And I keep it in the syllabus because of the intuitive and physical understanding it gives to how these processes work. It doesn't have to be used on a simple wedge. You could use it on any shape you care to postulate. Of course, it can't be on a shape that produces a shock wave that's so strong that the Mach number behind it is subsonic or not much bigger than one. We have to be in that hypersonic region where velocity isn't changing much with Mach number. So what we've got to do is look at the shape of any potential vehicle and find what flow deflection is caused. Well, we can get that quite simply geometrically, because if you look at a local flow deflection surface, you can see that dy by dx times your incoming velocity is a normal component of velocity to the surface. So that enables you to calculate in your flight vehicle how your piston velocity should have varied with time as your imaginary shock wave convex along the flow from the nose to the end of the vehicle. So I'll refer to our original figure here. We can explain it again. The surface of the vehicle represents a piston which is travelling transversely to the flow and pushing the gas out of the way. To get the piston speed, all we have to do is look at that geometry, calculate its slope, and we imagine that a shock wave, a shock tube, is convecting in an axial direction with velocity equal to a flight direction. We come up with a relationship for piston velocity as a function of time in our imaginary shock tube, which generates the flow. That's quite easy to do, provided the angles aren't that steep. Of course, there's not that much point doing that, because now what we have to solve is an unsteady piston velocity problem in a shock tube, which isn't actually as trivial as a constant velocity one. So we probably won't use it for this application, because it's a nice, simple thing to use when a surface geometry is straight. It's just a flat wedge, but it's a bit more complicated to pick up a complex geometry, so why bother? We won't use this application here. We'll save that for CFD and other solution techniques. There's another further development of this technique called blast wave theory, where you can actually include the effects of blunt bodies and regions near the nose where the Mach number isn't much bigger than 1 and the plane stations don't remain plane anymore. These are known as blast wave theory, and they're beyond the scope of what we're going to cover in this course. If we're looking at an axisymmetric situation, it's the same approach, except that you're not looking at a piston moving in a linear direction. What we have to consider is a radial expansion of a radial piston, if you like, pushing the gas out of the way, because in axisymmetric flow there's an extra dimension for which the expansion can take place. which complicates things a little bit. It's evident that this doesn't work in a low Mach number region, because when you get down to low Mach numbers, the flow really does drop dramatically from the flow of the rest of the vehicle, so plane sections won't remain plane anymore, and the basic principle we're relying on is no use. So remember that, only use it for sharp vehicles. Again, there's an error in boundary layers, because boundary layers, eventually velocity will drop to zero at the wall, so they're not going to work there. Hopefully the boundary layer is not a large proportion of the total flow field, so it'll work to get the flow properties outside the boundary layer and behind the shock, not for more detailed approach. And this technique can be modified to include the blunt body regions through a technique known as the blast wave theory, but that goes beyond the scope of what we're going to cover in this course.